All right. Move down. Okay. I'm just going to go through it one page at a time and see if you have any questions. Okay, so difference between organic and inorganic substances. When I think of organic, I think of compounds composed primarily of carbon. When I think of inorganic, we're not going to have carbon. So looking through the options, conducting electricity and not conducting electricity, that's metals versus nonmetals. And organic substances contain one kind of atoms, inorganic not necessarily, because you can have an organic compound with carbon, hydrogen, oxygen, nitrogen. So that's not correct. Living things and dead things, nope. That's the old definition. People thought that all organic compounds came from living things, but that's not true. Mostly carbon, other elements, that is the correct definition. And just chime in if you have a question. Difference between a metal and a nonmetal, that is the conducting of electricity, which is metals, and then nonmetals do not. On your periodic table, to the right of the staircase, not bordering the staircase, but to the right of those elements that border the staircase would definitely be the nonmetals. The three most common metals used to fabricate tools, that would be iron, aluminum, and copper. Can't make tools out of nonmetals. Not going to work with oxygen. And antimony, lead, and barium, that is gunshot residue. So the correct answer is iron, aluminum, and copper. Gunshot residue, and we just said it, antimony, lead, and barium. And of course, your symbols are SB for antimony, PB for lead, and BA for barium. Metalloid in the third period. Okay, so I want to make sure you're comfortable with navigating the periodic table. So let me go back to the periodic table. All right, so that's going to be page 2. Okay, so these are your periods. All right, so first period, second period, third period, fourth period, etc. And then your groups are your columns. Okay, all right, so back to the question. This is one thing that annoys me, again, about Blackboard is when you leave a page, all your notations disappear. So alkali metal in the fourth period. Okay, so alkali metal. So here is my fourth period, and group 1 are the alkali metals. Group 2 are the alkaline earth metals. And the other groups that have names are the noble gases for group 18 and the halogens for group 17. We don't have common names for the other groups. All right, so if we want an alkali metal in the fourth period, it would be potassium. What if we wanted an alkaline earth metal in the fourth period? Then it would be calcium, and so on and so forth. If we are asked for a metalloid, remember that your metalloids are the elements bordering the staircase, and they include boron, silicon, germanium, arsenic, antimony, tellurium, polonium, astatine. Aluminum, even though it borders the staircase, is not a metalloid, it's a metal. Questions? All right, so alkali metal, we just said in the fourth period, was potassium. The lowest energy radiation in the electromagnetic spectrum, so it goes from gamma, which is the highest energy, shortest wavelength, to radio, which is the lowest energy, longest wavelength. So the lowest energy would be radio. The highest energy would be gamma. Okay. EDX is energy dispersive analysis of X-rays, and it provides information about elements. So that would be D. And where is the EDX? What instrument is it housed in? Does anybody know? Good. It's inside the SEM. Excellent. The two phases that are present in any form of chromatography, including gas chromatography and thin layer chromatography and paper chromatography, is always stationary and mobile. A reaction that produces heat, if it produces heat, it's exothermic. If it absorbs heat, it's endothermic. And the others are just words that I made up. I actually really enjoy coming up with multiple choice questions. The 3 things necessary to start a fire, and remember the lab had the 4 things. They included chemical chain reaction, and they called it the fire tetrahedron. We typically look at the fire triangle, the more traditional look at fire. So it's 3 things: fuel, oxidizer, and heat. And extremely fast, so you have slow, fast, and extremely fast oxidations. Okay, and the slow ones would be something like rusting. Sometimes we just call it oxidation. The fast ones are going to be combustion or burning, and extremely fast would be an explosion. So for your oxidation reactions, those are going to be the ones. Oh, and extremely fast, I'm sorry, is explosion. Questions? In 2015, the motivation for the majority of arsons was unknown, but of those that were known, the main motivators were revenge and vandalism. The minimum temperature at which a substance provides enough vapor to burn. That is your flash point. And what is the minimum temperature that a combustible vapor will burn? And it provides the activation energy. It's another one you need to know. The minimum temperature at which the vapors will actually burn is called the what? Nobody knows that one? Ignition temperature. So the flash point is where your liquid will vaporize and produce enough vapors that now combustion can possibly happen. But just because you're at the flash point doesn't mean that the substance will burn. You need to provide that activation energy, which is the ignition temperature. That's going to put enough heat in to make it actually burn. And ignition temperature is always higher than flash point. Any questions on that? If oxygen suddenly enters a smoldering area, the soot and fire gases can ignite with explosive force as the rush of oxygen regenerates the chemical reactions and produces a backdraft. So you get a burst of pressure, and that can sometimes cause the structure of the building to break down, as we saw in the short video. Compounds comprised of only carbon and hydrogen are called hydrocarbons. So sometimes we show them as CXHY because they only have those 2 elements in different proportions. For example, octane has 8 carbons and it has 18 hydrogens, or butane with its 4 carbons and its 10 hydrogens. Those are all alkanes, and they're also called hydrocarbons. What investigators determine by measuring the depth and extent of charring is the duration of the fire. Controlled Substances Act 5 schedules were created, and all of the above, medicinal value, risk of harm, potential for abuse, are all taken into consideration. Any questions on that page? Identify the schedule. This one's a little tricky because you've got several. So you can definitely look at your notes for this one because it is not easy to memorize all of those schedules. And again, those schedules are based on medicinal value, risk of abuse, potential for harm. And so cocaine, because it did at one point have a medical use, it's actually a Schedule 2. Heroin, no accepted medical use, so it's Schedule 1. And the barbiturates, if you look, you'll see barbiturates are scattered between schedules. Some of them fall into Schedule 2, and that is the fast-acting barbiturates. And some of them fall into Schedules 3 and 4. So we'll just put 2 through 4. Marijuana, still a Schedule 1. And PCP, or angel dust, that one at one point did have, it was originally developed as an anesthetic. So because it did have a medical use at one point, it's Schedule 2. And so just look for, so definitely these are wrong because they put cocaine into Schedule 1. It's one of these two. They do have cocaine and heroin correct. And everything else is the same. This one's a little tricky, isn't it? There are so many barbiturates that they fall into different schedules. So we'll select D for that one. Questions? Which of the following is a characteristic of a physical dependence? When you're physically dependent, you definitely get withdrawal sickness when you stop taking it. And if you had a psychological dependence, that's more where you enjoy the experience, so you want to keep repeating it. So you get satisfaction and you want to keep repeating it. Those are both psychological signs of a psychological dependence on a drug. Okay, so producing a rush, numbing the senses, reducing pain, causing sleepiness. So reducing the pain and causing sleepiness would be narcotics. They also can produce a rush. Stimulating, so the key word there is stimulating. That's going to be a stimulant. So cocaine is one that people sometimes think is a narcotic, but it's actually a stimulant. All right, presumptive tests, those are the color tests that have different names attached to them, like the Scott test, the Marquis test, and the Duquesnoy-Levine. Those are all presumptive. The GCMS, the infrared, IR, and the TLC, thin layer chromatography, are all confirmatory tests. All right, so a chromatogram comes out of a gas chromatograph, and you get, as the bands are eluting or moving out of the column and they hit the detector, a peak is generated. So your first one coming out would generate a peak, and then nothing's coming out, nothing's coming out. Second band comes out, detector registers a peak, nothing's coming out, and then the third band comes out and detector registers a peak. The size and width of these peaks tells me the quantity or concentration of the component, but each peak represents a separate compound. And so this one, because it has 3 peaks, has 3 compounds. And the one that's present in the highest concentration is probably number 2. It's a taller peak than the others. Any questions on that? All right. Moving right along, now we are on the next page. State whether each of the following is a mixture or a pure substance, and specify whether the pure substance is an element or compound, or the mixture is homogeneous or heterogeneous. Potassium cyanide, that formula just is one compound, so that's a substance, and it is a compound. Gasoline, believe it or not, is a mixture of a lot of different hydrocarbons. And there are also some oxygenated compounds in there as well. So I'll just call those CXHYOZ. So you have a mixture of a lot of different chemical compounds. If you were to pour gasoline into a clear glass container, you would see that there's not a lot of solids. There's one phase. It's all one color. So when you have one phase, all one color, it would be homogeneous. Symbols and names. Antimony is SB. AS is arsenic. What is AR? That one's argon. Titanium, TI, but tin is SN. Those two people sometimes confuse, just like people sometimes confuse these two. Another set that people confuse is K and P. P is phosphorus, and K is potassium. It has the symbol K because it comes from the Latin word kalium. Electron transitions in an atom that cause light emission for the identification of elements. So you've got your nucleus, which has your protons and your neutrons, and then you have shells of electrons. And what happens when an atom is exposed to energy in the form of heat from a flame or electricity in an emission spectrometer, the electrons absorb that energy. And an electron is going to move from a lower energy level to a higher energy level. So you would say, okay, the electron absorbs energy and moves to higher energy level. What goes up must come down. So then after it moves up to that higher level, just like when you jump up in the air, it's going to fall back down. Instead of emitting the energy back as heat, and sometimes it does emit it as heat, but a portion of the energy is going to be emitted as light. So the electron falls back to the lower energy level and it emits the energy as light. Well, that's not just any light. That light has a specific wavelength, and the wavelength of the light, remember what wavelength is. Light comes in the form of waves, and the wavelength is the distance between peaks or troughs, and you can have a lot of different wavelengths of light. And for this process, the wavelength of the light is characteristic of the elements in the sample. So it identifies the elements in the sample. Each element is going to emit different wavelengths of light. That's why when you do a flame test, you get a different color of flame for different metal ions that you put into the flame. And that's why in fireworks, we have different colors of fireworks when we put different metal salts into the firework apparatus. So the wavelength of light identifies the elements in the sample. So that's what you need to do if you're asked to explain that process. And as far as the picture goes, you have your electron jumping up, and then the electron falls back down and it emits that energy as a wave of light. And why are they called metal salts? Because they're all formed similar to table salt, which, as you know, probably is sodium chloride and NaCl. That word salt is the word that we use to describe ionically bonded compounds that have a metal and a nonmetal. So we use that salt not just for table salt, sodium chloride, but for any salt. So if I wanted a yellow-orange flame, I could use sodium chloride. But if I wanted a green flame, I might use barium chloride. If I wanted a red flame, I could use what produces red? Calcium, and it doesn't have to be chloride, it could be calcium nitrate. So you can have different metal ions and different non-metal ions. All of those are what we call salts. They're made up of a metal and a non-metal. That's a good question, Carice. I think what I love about this class is you guys really seem like you want to learn. You're not just here to take a class and get a grade. You seem like you really love to learn, and you guys are the fun type of people to teach because you're curious and you like learning. All right, so how do we figure out protons, electrons, and neutrons? First, we need to find the element on the periodic table. And so definitely make sure you have your reference sheets handy when you're taking this test. So silicon is element number 14, and it has a mass for the most abundant isotope of 28. And so those two pieces of information, the atomic number and the mass number, are going to help me figure out protons, electrons, and neutrons. Okay, so the atomic number gives me the protons and the electrons. They're always equal to each other for a neutral atom. And then how do I get the number of neutrons? It is going to be mass number minus atomic number. So 28 minus 14 is going to give me the neutrons, and it's 14 in this case. For the smaller elements, you do tend to have similar numbers of protons and neutrons, but as you get to larger and larger atoms, you'll have a lot more neutrons than protons. Iodine, and I'm just rounding to the nearest whole number to get the mass number. So the atomic number is on the top when we find it on the periodic table. It's 53 for iodine. And again, mass number, the atomic mass is 126.9. I'm going to round that to 127 for the most abundant isotope of iodine. And so my protons and electrons are the atomic number. They're equal to each other because it's a neutral atom. And then neutrons would be 127 minus 53. And you'll see now you have more neutrons than protons. Plug that into the calculator, 74. And the reason why you have more neutrons when you get to larger and larger atoms is because the protons are packed very tightly in the nucleus of the atom, and positive charges would repel each other. So the neutrons buffer those repulsions and keep the nucleus more stable. Mercury and arsenic poison. So what are we asking here? Identify whether each of these is organic or inorganic. Well, they're talking about two elements that aren't carbon. They're talking about mercury, Hg, and arsenic, As. Those are not carbon-based, so I'll call those inorganic. On the other hand, arson debris, which is made up of wood. Wood, coming from trees, is made of cellulose, which is a polymer of glucose, and it's a carbon compound. It has carbon, hydrogen, and oxygen in it. Accelerant residue, we learned about accelerants being mainly hydrocarbons or carbon and hydrogen compounds. So both of these are based on carbon and hydrogen, and cellulose also has oxygen. Definitely organic because they're carbon compounds. That's why we introduced organic chemistry in the arson chapter. Do you guys have any questions? Could you do some more examples of identifying elements and compounds? Definitely. Why don't we finish this page and then I'll go into that. We only have one more on this page and then I'll go into that. All right, XRF, X-ray fluorescence. This is a small benchtop instrument that analyzes samples in the solid state and tells me the elements that are in the sample. So you shine your X-ray. You also have to have it very well shielded because you don't want your user exposed to any X-rays. So we shine X-rays on the sample surface, and then we have X-rays emitted by the sample. So the atom is absorbing X-rays and emitting lower wavelength X-rays. That tells me the elements in the sample. And what about the concentration? That's going to be a function of the intensity. Just like in GC, the size of the peak tells me the amount or concentration. The intensity of the X-rays will tell me the concentration. 3 elements: lead, antimony, and barium. All right, so I'm going to stop sharing this and I'm going to share the whiteboard so we can look at some element and compound examples. And I think the particle diagrams are really helpful for that. Okay, this is very difficult. Let me just draw it freehand. Okay, all right, so what are these different things? In this first one, I see what's happening. I need to reduce the size here. Okay, can you guys see that okay? In this first one, I have 2 different elements bonded together. How do I know they're 2 different elements? Well, okay, I should not have worked with this being enlarged. Okay, in the first one, 2 different elements bonded together. One of them is filled in, one of them is hollow. So that just represents 2 different types of atoms. And so that definitely is going to be a compound, but every unit in this sample is the same. So that's what makes it a substance and not a mixture. All right, in the second one, I'll just type above, we have just single atoms, and they're all one type. And so because of that, in the second one, we're just going to call that an element. And it's, of course, a pure substance. All right, the third one is a little bit different. I have some single filled in atoms, and then I have some compounds that are made up of 2 atoms bonded together. So it's a mixture. Whether it's homogeneous or heterogeneous, you can't tell from particle diagrams, but we can definitely tell that that one is a mixture because we have the single atoms filled in, which are an element, and then we have the compounds where you have the blue and the white atoms bonded together. And for this last one, a little bit different. We have two atoms bonded together, but they're the same. And so when you have the same two elements bonded together, that is a diatomic element. And so in that diatomic element, our sample is not a compound, it's an element. And both compounds and elements are pure substances. So that's kind of an overview. Any questions on that? All right, so let's say you had, oh, highest wavelength does refer to the longest wavelength. Yeah, feel free to ask me any of your questions. All right, so let me go over a little bit more of the identifying elements and compounds. All right, let's look at these examples. All right, so the first one, potassium chloride. This is a unit, okay? When you're given a formula like this, this is a unit that's made up of two different elements, but they are chemically bonded. So you can call those chemical units that are bonded together. And that definitely is going to be a compound. And compounds are one type of pure substance. So it's a pure substance and it's a compound. Soil, as you know, especially topsoil, is a mixture of organic matter, inorganic matter, lots of different living organisms, decaying organisms, broken up bits of rock. There's some water mixed in there, different phases. So that the fact that there are different phases, you can see different colors, you can see solids and liquids, makes it a heterogeneous mixture. Aluminum metal, we only have one kind of element. And that will be an element and a pure substance. Any questions so far? Okay, I need a visual in this one. I've got a container of water and there is some salt, which may or may not be dissolved, but then there's sand. And I know sand is not going to dissolve, so the sand's going to be sitting on the bottom. And the salt may be dispersed or dissolved depending on how long it's been sitting there. So I've got some solids at the bottom, and then I have a liquid phase. So the fact that we have multiple things in here, sand, in case you didn't know, is silicon dioxide, but it also can have impurities in it. Salt is sodium chloride, and water is H2O. So we have different substances. It's definitely a mixture. And the fact that there are different phases means that it is heterogeneous. If the problem had said salt dissolved in water, it would be a homogeneous mixture. You guys know what air is composed of? What is the main component of air? Close. There's not much hydrogen because it has such low density. Nitrogen for sure. Oxygen, and the nitrogen is 78%. Oxygen is about 21%. And you might be thinking the elements that are in air, you do have some water vapor, which varies from 0 to 5%. And that's where the hydrogen comes in. It's got 0.9% argon, and then it is 0.1% other gases. So how would you classify air? Is it a substance or a mixture? And yeah, the other would be CO2, which is about 0.06%, I believe. Yep, definitely carbon dioxide's in there. So is it a substance or a mixture? It's a mixture. Now, assuming we're not in China or India where they have a lot of air pollution, if you're looking at the air here, would you say it's homogeneous or heterogeneous? Yes, it's pretty uniform, clear and colorless. If you have a lot of particulates, if it's hazy, then you might start saying maybe heterogeneous. Very good, guys. So Ryan, did that answer your questions about that? Were there any other examples you wanted me to do? Okay, perfect. That'll definitely be on there. So I'm glad you asked that one. Do you guys want to keep going through the exam? Okay, where did we leave off? We finished page 9 and we're on page 10. We have 11, 12, 13. Boy, that's a long practice test. We need to get to page 14. Okay, let me blow this up again. Simplest substance known that provides the building block from which all matter is composed. That would be an atom, but you could also say element. Either of those is fine. The atom is the individual particle of an element. 2 or more of these chemically combine to form a compound. If you said molecule, that would be okay too. And an analysis that involves identifying components in a sample. If you're identifying them, that's a qualitative analysis. And if you are determining concentration, that's a quantitative analysis. And I like this question on the waves. We have 4 different waves shown here. Which has the highest wavelength? Remember, wavelength is the distance between peaks. And we have the largest distance for wavelength number 3. Frequency is how many peaks repeat themselves per unit time. And the one with the most peaks is number 4. And those 2 properties are inversely related. So higher wavelength leads to lower frequency. Shorter wavelength leads to higher frequency. This is a gunshot residue particle here. That's what it looks like under an SEM microscope. So gunshot residue, characteristic looking particle. And the shape of it is part of the identification, and then the elemental composition confirms it. So that was taken with a scanning electron microscope. You can tell it's an SEM. If you were able to see this, it would be high magnification, greater than 1000. And the other thing is you get these gray shaded images that just shows the surface. So that's the other clue that you're looking at an SEM image. And that's scanning electron microscopy, scanning electron microscopy. This instrument, the argon plasma, is the key here. ICP-OES, you can look that up. It stands for Inductively Coupled Plasma Optical Emission Spectroscopy. You need to dissolve your sample in acid because the acid solution is what's going to be in here. The reason you dissolve it in acid is going to oxidize and ionize and dissolve all metals in the sample. And you're typically looking for the metals. That's why we dissolve it in acid. So the acid puts all of the metals into ion form. If you're doing a flame test, you need the same thing. You need a dissolved ion. An ion is just a charged atom that is very soluble in water. So once you get them into the form of ions by adding acid, they're well dissolved, and they then are going to be able to go into the plasma very easily. And once they're in the plasma, they absorb the energy from the heat of the plasma. Remember that plasma is like 10,000 degrees Celsius. The heat causes the electrons to jump to a higher energy level. When they fall down, they emit light, and we're going to capture that light with the detector, and we're going to measure the wavelength and the intensity of the light. The wavelength will tell us the elements in the sample. The intensity will tell us the concentration of elements. We need to calibrate it with solutions of known composition. So you create calibration curves. If you watch the video of the scientist explaining that process, she showed you calibration curves. And the cool thing is it will instantaneously analyze over 20 different elements at one time, because you'll run a mixture of all those elements in your calibration standards. You'll have your cal curves set up in the computer. And once you put your samples in, the computer will very quickly calculate which elements are there and what their concentrations are. Page 11, balancing equations. That's another skill that can be challenging. So how do I do it? I go from left to right. I start with carbon. I have 5 carbons. The subscript after the element tells you the number of that element in the sample. So 5 carbons. And I need to have the same type and number of elements on each side. Over here, I only have 1 carbon. So I would put a coefficient of 5, which means I now have 5. I can't put a subscript after the carbon because then it would no longer be carbon dioxide. It would be pentacarbon dioxide, which isn't a real compound. So we can have multiple carbon dioxides, but we can't change the identity of the reactants or products. Next, I move on to the next element, 12 hydrogens. Well, on the right, I only have 2 hydrogens and I want 12, so I'm going to multiply that one by 6. Now I have 12 hydrogens. 6 times 2 is 12. Last but not least, oxygen. I have more on the right, so I'll count those first. 5 times 2 is 10, plus 6 times 1 is 16. 16 oxygens on the right. I only have 2 right now. So what can I multiply 2 by to give me 16? 8. Now I have 16 oxygens on both sides. The one that's blank is going to end up being the number 1. So there's 1. And by the way, what's the name of this compound? Pentane. So make sure you're familiar with your 10 alkanes: methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonane, and decane. All right, so that's pentane because it has 5 carbons. They all end in ane, and it's being oxidized. You could say that's a combustion or an oxidation reaction. Pentane is reacting with oxygen to produce carbon dioxide and water. For every 1 pentane that reacts, we have 8 molecules of oxygen reacting, 5 molecules of carbon dioxide formed, and 6 molecules of water formed. And that equation is balanced. So we are following the law of the conservation of mass, which says in a chemical reaction, you can't create or destroy matter. Questions? All right, arson scenario. Large home, 50% of the structure is destroyed. Heavy burning on the floors, that starts to indicate arson. Streaks of burnt area. So heavy burning on the floors, streaks of burnt areas, that means that they were pouring accelerant between areas. Little burning on the walls, so we probably don't have an electrical fire. solvent-like odor. I think this is the same example we did in class. I need to mix up my examples. So definitely arson for those reasons. Arson debris, sealed metal can. And that way we are going to preserve the volatile accelerant residue. We don't need to worry about mold or anything. We're not running DNA. Mainly we want to preserve that accelerant residue, and that's why the can needs to be sealed. We'll use metal or glass because they're inert and unreactive toward these solvents. Don't want to use plastic because these accelerants could react with the plastic. Questions? Okay, to figure out whether molecules are structural isomers, I need to write out the molecular formula. I need to count the carbons and hydrogens. 1, 2, 3, 4, 5, 6. And then I count up all my hydrogens and I find out that there are 14 of them. Now I do the same thing for the next molecule. 1, 2, 3, 4, 5, 6. So there's also 6 carbons. Let's count up the hydrogens. 3, 6, 7, 8, 9, 10, 11, 12, 13, 14. Same molecular formula, but their structures are different. This one has 6 carbons in a row, and this one has 4 in a row with 2 branched off the middle carbons. So they are structural isomers. And you would explain they have the same molecular formula, but different bonding pattern. That's what structural isomers are. Let's say you looked at the molecular formulas and they were different. Let's say one was C6H14 and the other was C5H12. In that case, they would definitely not be isomers. They're completely different, unrelated compounds. But if they have the same molecular formula, but different bonding patterns, they are structural isomers. What if they have the same formula and the same bonding pattern? Then they're just the same compound. Okay? Questions? GC, gas chromatography, testing for the presence of accelerant residues. Retention time is the identifier if you don't have a mass spectrometer. Retention time is relatively unique for each compound, although you sometimes have 2 different compounds with the same retention time. If you have a good separation, you should be able to get different retention times for each compound. Concentration from the peak's area, you could also say height or size or intensity. Make sense? Heated headspace sampling, so you've got your vial with a septum cap and you're going to put your arson debris in the bottom and you're going to heat it, and you're just going to heat it gently. That's going to cause vapors to travel up, and the vapors are what we're going to sample with our syringe. Okay, so stick your needle through the septum, pull up some of those vapors and inject them into the GC, and you can look and see, is there gasoline or kerosene or paint thinner in those vapors? Questions? On the GC diagram below, identify the components. Number 1 is your helium tank, and that is your mobile phase. So if you had said helium tank or mobile phase, that would be fine. Number 2 is the sample syringe. So you can say sample or syringe. Number 3 is the injection port. And number 4 is the column. Questions? Okay, so you don't need to memorize these different tests. What you want to do is just look on the table. So we have a purple Duquesnoy-Levine and all the other tests are negative. When I look at my table that's on page 2, if I get a purple Duquesnoy-Levine or violet, same thing, marijuana. So that's a positive result for marijuana. Definitely we'll have one of those on the test, so just make sure you have that reference sheet handy. And this one, can you just look at your notes? IR spectroscopy, you're shining infrared light on the sample. And this is used for molecules. Different portions, different bonded atoms in the molecule are going to absorb different wavelengths of infrared light. And so you're measuring percent transmittance as a function of wavelength. And you'll have peaks, which are the downward things, and you get a very unique pattern of peaks for different molecules. So to explain how the instrument works, we have a source of infrared light shining light through the sample. We are going to measure the absorbance of that light as a function of wavelength of light, and we get our IR spectrum. The pattern of peaks in the IR spectrum is unique for a given drug sample. We say it's just like a fingerprint for an individual person. The pattern of peaks is unique for an individual molecule. Questions? Thin layer chromatography. So you're going to divide the retention time by the distance of the spot by the solvent distance. And that would be 0.62, which is closest to cocaine. Be on the lookout for something like this on your bonus question, okay? Be a little bit different, but a similar idea. All right, so look for charges. If you see charges, positive and negative charges, that is your what we call a hydrochloride salt. And it's formed by taking the free base or the free amine and reacting it with HCl. Just enough HCl to make it into a salt. We don't want any extra hydrochloric acid hanging around. A free nitrogen with a lone pair on it is a free base or a free amine. All right, the two properties we're interested in are water solubility and volatility. Salts, just like table salt, sodium chloride, are soluble in water. But the free amine, because it has such a large portion of the molecule being very nonpolar and organic based, kind of like oil doesn't dissolve in water, these large organic molecules do not dissolve in water. You have to make them ionic to make them dissolve. And then volatility is the opposite. So things that are soluble in water don't evaporate easily. Salt does not evaporate easily. And things that are insoluble in water, like gasoline, does evaporate easily. So the free base is volatile. How would you ingest those? If it's water soluble, it'll probably be by mouth. And if it is volatile and not water soluble, it would either be smoking or inhaling. So those are the two different forms. A lot of drug molecules have the nitrogen group on them. Therefore, they can be interconverted between free base or free amine and hydrochloride salt. The leading cause of U.S. injury deaths in 1999, motor vehicle accidents. Injury deaths. This is so interesting to me how it's changed in the last 20 years. 2015, it became drug overdose. The top two drugs, can anybody refresh my memory on those top two drugs that cause accidental death? All right, so the top two drugs in 2015 were at 31,181 medications. And in the footnote, it says prescription drugs, things like, it just says unspecified narcotics. The second one is heroin. So prescription drugs and heroin. And we all know that some of those prescription drugs are things like oxycodone, fentanyl. And I think today they do a better job of breaking it down by drug. The precursor used to synthesize methamphetamine is pseudoephedrine. Yes, that is the great cold medicine they have behind the counter now at your pharmacy. You don't have a prescription to get it. You just have to show your driver's license. And they need your driver's license because they're limiting how much one person can buy, and they're tracking how much you're buying. So if you're buying 5 packs of it every week, you might start to become suspicious. But they're doing that because of the methamphetamine epidemic, where people are using it to synthesize methamphetamine. Besides the problem of illegal drug use, what other hazards? We have flammability of some of the chemicals and the risk of fire and explosions. We also have toxic residues that are left behind. All right. When drugs are put into classes based on their effects on the body, those with high potentials for physical and psychological dependence include, so we have narcotics, stimulants, and depressant. Most of the hallucinogens some of them are physically addicting as well, but several of them are just psychologically addictive. Morphine comes from the poppy plant. Marijuana comes from the cannabis plant. Mescaline comes from the peyote cactus, and LSD comes from the ergot fungus. Those are all natural products, so they're good for you, right? No, they're not good for you. The most abused drug in Western countries, alcohol. Still the most abused drug. It's over the counter. You just need to be 21 to buy it. And it's such a part of social life that people think it's okay, but it is highly addictive. Alcohol, Bureau of Alcohol, Tobacco, and Firearms regulates alcohol.